enhance control, operations and maintenance in chemical processes
as well as to explore pivotal phenomena in industrial chemical operations. Presently, his research is centered on pioneering next-generation battery technologies, including zinc air, zinc ion, and zinc iodine batteries. With a prolific academic record, Suratep has penned over 200 articles in esteemed journals and is a regular presenter at international conferences discussing energy storage innovations. Professor Suratep, it's indeed our pleasure to welcome you on this auspicious day, on the second day of our conference. We are overwhelmed by your presence for the knowledge sharing about the recent challenges and the need of the hour for the environmental or climatic change, and especially your area of interest about the batteries or the technology that is related to the batteries and energy conservation. Thank you so much for joining us, and the stage is to you. Please take on. Thank you so much. The stage is for you, Professor. You can. Professor, are we audible? You are muted, I believe.
Yes, I can hear you, but well,
Yeah.
yes, I can hear you.
So now you can, the stage is for you. You can start your deliberation.
Thank you very much. So, well, let me share my slide. Sorry. Okay, I believe that while you see my screen, right? Colorful screen.
Yes.
Okay, thank you. Thank you very much, well, for this opportunity. And sorry that I cannot present there. I cannot attend in person, but well, you know, maybe next year. Okay, I'm Suratep Kyohom from Chulalongkorn University. And today my talk is on zinc ion battery. I think that, well, you listened from, well, my colleague presentation previously about zinc ion batteries, right? So, well, let me start my talk again from this picture, this photo taken from space. And of course, the bright spot represent the place where electricity it's intensely consumed. So when you see the light, you see the modernity, you see the modern world, and well, when you see light, you see the modern world, and where you don't, there is one of two conditions: either nobody living in that area, or it hasn't been electrified yet. So for such a case, there is no more precious gift you can give those people than electricity and access to electricity. But we want sustainable electricity, and there is going to be carbon-free electricity. Wind, solar, but they are intermittent and they are incapable of being base load, fully integrated to the power grid. And energy storage is a key in terms of cost. You see that solar and wind win the race, and they are about 3 times cheaper than biomass. However, as we have to respond to the question, what should we do when the wind is not blowing and the sun is not shining? Yes, energy storage is the key. Though technologies regarding harvest and conversion of renewable energy are significantly advancing, we can effectively produce electricity by wind turbines and photovoltaic cells at a fraction of cost. We can produce electricity and feed to the power grid. However, there's no inventory in power grid. Even we install more PV, more solar cell, but we cannot respond to the electricity need during nighttime. To address this issue, we need energy storage system. So batteries are a storage system for electrons. We need two electrodes having different electrode potentials. Of course, highly reversible reaction is preferable. If we want to build a battery having very large capacity, we cannot rely on scarce or rare materials, rare metal. If your technology use rare metals such as platinum, later you will have problems when we scale up the system. In my lab, I won't allow students to touch it. Zinc is a good option, as zinc is the fourth major production metal. The production of zinc is over 12 million tons per year. Zinc is cheap and abundant, and it has a stable supply chain. Moreover, it has variable redox potential, high stability, and a high capacity. On top of that, zinc is 100% recyclable, and the recycling technologies are already available. So zinc has been used a long time ago in primary batteries. We have zinc carbon and alkali batteries. Both systems are very common. Both systems use zinc and manganese oxide as active materials. For zinc carbon batteries, ammonium chloride solution is used as an electrolyte. In comparison, potassium hydroxide is used in alkali batteries. So the production and consumption of zinc carbon and alkali batteries are huge. We do not much pay attention to primary batteries. We focus on secondary batteries. There are a number of possibilities for rechargeable zinc-based batteries. There are rechargeable alkali, zinc nickel, zinc air, and zinc bromine batteries. Zinc ion batteries are also under development and receive much research attention recently. And the charge storage mechanism of zinc ion batteries rely on two processes, namely the intercalation of zinc ions at the cathode, also called intercalation material, and the dissolution deposition of zinc at the anode. Theoretically, zinc as an electron source can deliver a large capacity of 820 milliamp-hour per gram of zinc via dissolution reaction. In most cases, the capacity of zinc-ion batteries have been limited by the lower capacity of host material. To date, several kinds of host material have been undertaken in the study of zinc-ion battery. Several aqueous zinc-ion batteries recently proposed are seen to be very promising both in terms of performance and cyclability. However, up to now, no zinc-ion batteries have been recommended for the commercialization battery market. This outcome points to the fact that there are a number of batteries, of barriers, which limits the application in practice. The issue with the aqueous zinc-ion battery system are as follows. First, hydrogen evolution reactions, HER. Since water is protic solvent, which can dissociate and provide proton, the contribution of proton upon charging is unavoidable. Thus, the proton reduction reaction is considered to be a competitive reaction, resulting in lower charging efficiency and excessive pressure within the battery package. In practice, the high concentration of zinc salts, as well as the addition of zinc of some inhibitor, can suppress HER. The next one is dendrite formation. Dendrite formation is not such a new issue in battery research. especially in the system where metallic anodes are used. In aqueous zinc-ion batteries, zinc dendrite can be formed due to the uneven zinc-ion flux and electric field above the zinc anode, and can lead zinc-ion battery to failure because of short circuit. Moreover, the operating conditions such as the current density and area capacity involves the evolution of zinc morphology and can further lead to the formation of dendrite structure in long-term cycling. And the next one is corrosion of zinc, which is related to self-corrosion of zinc. Well, actually, it's a different scenario from HER due to the fact that aqueous my acid electrolytes always contain protons, and the proton has a higher standard potential than zinc. These protons can draw electrons from the metallic zinc. Accordingly, zinc is corroded and changed into zinc ion, and pressure is built up within the cell due to the hydrogen gas produced. And the last one, passivation, which is one of the issues concerned with aqueous zinc ion development, is the formation of passivation layer, which can reduce the performance of aqueous zinc ion battery in long-term cycling. Okay, so in our lab, we use several techniques to stop those issues, to mitigate those issues. The first one is, well, we use hybrid electrolyte. Hybrid electrolyte, it's the electrolyte containing water and other solvent. For example, in this case, in our recent work, we use water, a mixture of water and TEC-DME, tetraethylene glycol dimethyl ether. Okay. And of course, we need zinc salts such as zinc OTF, zinc trifate. And this solution can modify the hydrogen bonding and can engage in the solvation arrangement of zinc ions. And this modification weakens interaction of water molecules and between water and zinc ion battery. Then we can suppress the activity of water molecule in the electrolyte. Okay, or the next one, we use polymer gel electrolyte. In this one, we use phosphonated graphene oxide modified polyacrylamide hydrogel electrolyte for solid-state zinc-ion battery. In this case, well, we test it with the manganese oxide cathode, and it showed very good performance, I mean, in terms of stability. And the next one, we work on, well, fabricate the artificial solid electrolyte interface. In this case, we fabricate a layer of a ACI solid electrolyte interface by using covalent organic framework. But in this one, well, you can refer to our article. There is a layer of a covalent organic framework protecting zinc metal, and this layer allows the zinc ion to pass through this layer, but blocking the water. Then we can reduce the activity of water activity at the zinc surface, then suppressing the hydrogen evolution and other, well, issue regarding the HER. And another idea is, well, to instead of using the aqueous electrolyte, we can replace aqueous electrolyte by using the non-aqueous electrolyte. You know that those results, I mean, most of the results are, well, are contributed by the activity of water or activity of proton, because our electrolyte contains proton. So if we replace the electrolyte with other solvent without free proton, then we can effectively solve the problem. So we can use organic electrolyte or room temperature ionic liquid, or even deep eutectic solvent. So by using polar protic solvent instead of water, the polar protic based electrolyte can be formed using the mixing. It's a mixture of zinc salt with polar protic solvent. Zinc salt can be, well, zinc trifate, zinc TFSI, or zinc perchlorate. And due to their non-protonate nature, so the polar protic-based electrolyte can eliminate HER effectively, and then we can suppress the self-corrosion of the zinc anode. And the most polar protic-based electrolyte possesses a wide stability window. What does it mean? That it means that we can use we can stabilize the zinc cycling. Also, it allows us to use a high voltage the cathode. Okay, so most polar protic solvents display poor thermal stability and are flammable. So we should select the right one. I mean, most polar protic solvents are harmful to human and then environment. So you should consider that. And due to their limited solubility of zinc salt and high molecular weight, most polar protic solvents exhibit inferior transport property of zinc ion compared to aqueous electrolyte. That is non-avoidable. And most polar protic solvents face issue regarding the large dissolution penalty of solvated zinc upon intercalation reaction. And it leads to, smaller discharge voltage of the zinc ion batteries. So what we work, our work focus on one organic solvent. It's a dimethyl sulfoxide based electrolyte. We call it DMSO. The DMSO is polar protic solvent, of course. It's non-proton donor solvent. Okay, so then we don't have free proton in the electrolyte. And it has high dielectric constant and wide electrochemical window. And also it has a high boiling point, okay? And less toxicity, which means, it can be translated to, more environmental friendly, okay? By using DMSO, we can increase the stability. You can see from the Coulombic efficiency at different cycle number, and you can see that by using DMSO based solvent, it's quite stable, and the Coulombic efficiency is close to 100%. Then it translates into we can suppress all the side reactions. Okay, in water-based electrolyte, most of the time we will see that hydrogen build up inside the cell package, and it leads to explosion of the cell package. But in case of DMSO, no such scenario occur. Okay, and by using DMSO, we can control the morphology of the zinc plating. If we look at the over potential of the dissolution and also plating and stripping of the zinc electrode, we see that it's quite at the beginning. Maybe it has higher over potential when compared with aqueous electrolyte. However, once we perform cycling at certain current density for a while, it approach to the same over potential. Okay. So if we look at the HER and self-corrosion comparison between the aqueous electrolyte and DMSO electrolyte, we perform soaking tests, and you see that we soak it for 24 hours and no DMSO. In DMSO electrolyte, no hydrogen bubble occur at the surface of zinc. Also for cycling tests, you see that in case of DMSO electrolyte, we cannot observe the hydrogen bubble. That means we can effectively suppress hydrogen evolution reaction. And if we look at the mechanism of the intercalation process at the cathode, you see that from the XRD result, it indicates that we have a layer-to-layer transformation of manganese oxide. That means before the intercalation occur, the manganese oxide is a layer type, and then after we insert or intercalate zinc ion into the manganese oxide layer, it's still layer type. Okay, and we did not observe the phase transform of manganese oxide to manganese oxyhydroxide, which is this is the side reaction which kills our battery. Okay, and such a mechanism is similar to that of zinc acetone nitride, zinc TFSI, and in delta manganese oxide system. Okay, so you see that while we can stabilize the system by using DMSO-based electrolyte. However, while we want to, because the performance in terms of current density and discharge rate, well, it's much less than in case of aqueous electrolyte. So we work further on the development, enhancement of the performance. Okay, in this case, we study the mechanism of the intercalation and also the role of water. Okay, role of water in the zinc ion battery with manganese oxide cathode using DMSO-based electrolyte. Okay, so we test electrolyte with containing different ratio of water. We see that, well, once from dry electrolyte or DMSO-based without water in the electrolyte, if we by introduce the water molecule into the DMSO electrolyte, we can largely improve the performance. Okay, we test the electrolyte containing 1, 5, and 10 to 20% of water. Okay, in the electrolyte, and we found a huge improvement in the performance. Okay, in the same system, and the capacity almost matched with the aqueous zinc manganese oxide battery. Okay, which is larger than 200 milliamp hour per gram. And if we look at the stability, of course, the system is still stable while we improve the performance of the battery. Okay, so while cyclicity results of zinc manganese oxide cell having DMSO electrolyte having, well, several ratio of the water are showing here. And the 5% sample possess the highest capacity and all water percentage exhibit highly stable cycling trend upon 500 cycle. And while if you look at the GITT, okay, in titration result, discharge over potential of the 5% sample is much lower than in case of dry solvent. It's 0% weight of water. And now, while we look at the possible role of water in enhancing the performance, okay, from previous literature, there are 3 ways, from the suggest in this paper. The first one is on the reduction of dissolution penalty with the substitution of water molecule in the zinc solvate shell, or it can be, well, the result from improved transport property, such as the ionic conductivity, transference number, or it can be, well, attributed by the change of the mechanism of the charge storage mechanism in the manganese oxide. While our colleague used MD simulation of water, okay, and we test the role of water, and we see that during 1 to 10 weight% of water in DMSO electrolyte, there is no contribution of water in the solvate shell of zinc ion. And so substitution of even 1 molecule of water was observed at 20% of water only. So it translates into, well, the first one, reduction of dissolution penalty via the substitute of water molecule in the zinc solvate shell. This cannot be happen in the electrolyte containing water less than 20%. So the first hypothesis is not true. Okay, so we further check the other hypothesis on improved transport property and the change of the charge storage mechanism. Well, we look at the transport property of wet DMSO electrolyte. And as the water contents increase, we see that the transport property of zinc ion diminished. So the transport property doesn't increase with the increasing of water content. So it's go opposite way. And Raman result also confirmed. Raman result indicate the formation of hydrogen bond between the hydrogen water and the oxygen of dimethyl to create dimethyl water, dimethyl bond. And the hydrogen bond is not good in this system, okay? So the formation of aggregated dimethyl water, dimethyl molecule, can reduce mobility of solvent, zinc ion. So again, the second hypothesis is not true because by introducing water, it doesn't improve the transport property of the electrolyte. Okay, now we look at the last one, change of the charge storage mechanism of manganese oxide. So we use SAN and XPS. SAN and XPS result indicate the higher manganese redox in the 5% sample than in the case of dry solvent. And we see that the addition of water can improve the utilization of manganese oxide upon charge storage reaction. Okay, and the contribution of zinc ion in the charge storage process cathode is confirmed by XPS also. Also, we use Raman. Raman result indicate a layer-to-layer transformation. It's just similar to what we observe in the case of dry solvent, dry dimethyl electrolyte, I mean, yeah. So for layer-to-layer transformation occur in both 0% dry electrolyte and 5% sample. Okay, so now we look at XRD and XPS result. XRD and XPS result of the manganese oxide collected from dry electrolyte from 0 to 5% sample at the discharge stage. Okay, so for dry solvent sample, the transformation, we observe the transformation of manganese oxide from Burnett side to Burnett side. Okay, it's a layer type to layer type. However, when we introduce water into the electrolyte, in the case of 5% water, dimethyl electrolyte, we found a significant increase in the water contribution. So again, it's still layer to layer, but however, once the water molecule and also zinc ion insert into the manganese oxide, we observe that the manganese oxide change from Burnett side to Buserite. Okay, so for 5% sample, a very minimal change in the radial distance of manganese to oxygen and manganese compared to that of in case of dry solvent, dry electrolyte, indicating lower electrostatic interaction between zinc ion and oxygen atom of manganese oxide. Okay, so it promotes better diffusion of zinc ion in the manganese oxide structure. So let me conclude. So the model is, well, in case of dry dimethyl, we see that upon intercalation, we see that, well, the manganese oxide still layer type. It's Burnett side to Burnett side. However, in case of electrolyte containing water molecule, the water molecule also intercalate into the manganese oxide. So we observe water molecule intercalate and well, widen the interlayer spacing between manganese oxide layer to, yes, and it changed from 7 angstrom to 10 angstrom in case of zinc Burnettsite. So it reduced the electrostatic force of a
audio. Professor, just a minute. There is some glitches in the audio.
Having dry electrolyte and can cycle at least 3,000 hours without the failure. Okay, so I introduce you the development of zinc ion batteries and the enhancement in performance of the dimethyl-based zinc manganese oxide battery relies on the role of water in reducing the interaction between zinc ion and manganese oxide layer, resulting in better solid phase diffusion. Redox of manganese oxide upon intercalation reaction is enhanced. And 5% in 0.3 molar of zinc triphate in the metal can improve the performance of such a system, whereas the stability is still retained. Thank you very much. So if you have any questions, I'm more than happy to entertain your questions. Thank you.
Thank you, Professor Suratep, for the wonderful deliberation on zinc-ion batteries, using water as an electrolyte. And I'm sure that the audience was really inspired by the newer research, what you are doing.
Hello?
And
Do we have questions from the floor?
yes, the question is open to the floor. If there is anybody can get the microphone, and I would like you to ask if you have any doubts. Professor, is it audible? Professor Suratep, can you hear us?
No, I can hear you, but not others.
Yes, I'll get you.
Hello. Yes, Professor. You said for 0% sample, the transformation between Bernstein to Bernstein structure. That means no change in structure morphology, no, for 0% of water. That's true?
Yeah, from 0% from disolvent, nothing changed. It's Burnett side and Burnett side, right? Before, I mean, the charging state and discharge state, it's still the same. It's Burnett side, right? In case of, electrolyte containing water, of course, it's layer type, but it's not Burnett side. It's Bucerite with different interlayer spacing. Just that.
Thank you, sir.
Anybody else? Yeah, there is one more.
Thank you, Professor, for your nice talk and informative talk. My question is about the basic, compared to lithium-ion batteries, the charge transferability, because the zinc, we know it is a molecular high weight, how it is possible? My first question, and also compared to in terms of safety-wise, I hope compared to lithium, this would makes better, I think. Please comment on this.
Okay, I'll give you more information regarding safety first. For safety, it's quite safe for this system. If you choose to use aqueous electrolyte, of course, aqueous electrolyte can be used. And in aqueous electrolyte, you cannot burn it. That means it will not catch fire. Okay? But even you use the non-aqueous electrolyte, of course, if you want to burn it, of course, you can burn it. But it's not easy to catch fire. Okay? Moreover, zinc is quite stable, so it's not tend to catch fire in that case, and it's not explosive. And for the mechanism, your question is on the mechanism, right? The mechanism of zinc-ion battery, or can you repeat your first question again?
1 minute, Professor. He is on to the line.
Yeah, I was asking about the mechanism of zinc-ion battery. Is it similar to the lithium, how it is the intercalation taking place, or it is how far?
Okay.
How the in terms of kinetics, I was asking.
Okay. So, for zinc-ion battery, if we look at the anode, it's totally different, because in lithium-ion battery, we have intercalation for both anode and cathode, right?
Yes.
However, in case of zinc-ion battery, at the anode, it's not intercalation at all. It's plating. It's a plate, stripping and plating, okay? However, at the cathode, the mechanism, the basic mechanism, it's rely on the intercalation, the intercalation. In this case, it's more or less similar to lithium-ion battery, okay? Yeah, it's intercalation. However, if we look at the kinetic, lithium-ion is oxidation state is just only 1, right? Plus 1.
Yes.
However, in case of zinc, it's plus 2. So we have more problem on the electrostatic force, electrostatic charge. Okay, so the intercalation seems to be lower, slower than in case of lithium-ion battery. Also, the diffusion of zinc it's much slower than in case of lithium-ion battery. Yeah, because of that reason.
Okay, thank you, Professor. Thank you for your...
Thank you.
Professor, there's one more question. Can you please go to the camera, sir?
Hello, Professor Surdeep, how are you?
I'm good, thank you.
Okay. After modification, did you see any hydrogen evolution in the electrolyte after modification?
No, up to 20% we can suppress activity of water. That means, well, we can mitigate all the activity of water at the ratio of water below 28%. Okay. However, I cannot say that, well, if you increase water content to be more than 20%, you can, the system is still stable. I cannot say that because we test at only that 20%. Okay?
Okay. Thank you.
Yeah.
Anybody else? Audience? So, Professor, with this, I think we are coming to an end of your deliberation. Thank you so much for your wonderful deliberation and a big eye-opener for the present needs of the global challenge, making things easier to use our natural
Sorry,
resources.
I cannot hear you. Can you speak to the microphone?
So, Professor, can you hear me now? Professor, can you hear me now? Audible now. Can you hear me?
Yes.
Yeah, that's nice. So thank you so much for your wonderful deliberation, especially on the zinc on batteries and the electrolytes that is to be used, especially about you deliberated about water. And I hope your research will be a big eye-opener in our country and our people and the researchers over here. And we wish we have you here personally for the next time, so that it will be of more encouragement for our young researchers who are here, who have joined here to hear your lecture, as well as in various other parts of the country by online. Anyhow, on behalf of Vinayaka Mission Research Foundation and Annapurna Arts and Science College, I would like to thank you once again for having come online for this wonderful deliberation on this morning. Thank you so much.
Thank you. My pleasure. Yes. And well, of course, I will book my, I will mark my calendar next year. Thank you. Thank you very much.
Thank you so much.
Thank you so much for your presentation, sir. We now request Dr. V. Anbalagan, sir, to felicitate Professor Dr. J. Babyjohn, sir, Principal, Vinayaka Mission, Shankaracharya Dental College, Salem. Thank you so much, sir.
From now, the parallel sessions will be starting. One parallel session will be happening here in this Annapurna auditorium, and another one will be continued in Annapurna Lecture Hall 1, which is in the hospital building, 2nd floor. Sessions that will be handled there, the professors are Professor Dr. A. Kadrivan sir and Professor Dr. K. Shaktipandi sir. Their sessions will be going on in Lecture Hall 1. Professor Dr. Anand sir and Professor Dr. M. Asha Jonsi ma'am will be handling it here. All the delegates who will be taking part in the concern sessions, please go to the respective halls as soon as possible so that we'll be proceeding with the next session soon. All the delegates, for another information, the third session that will be between 11:30 to 12 p.m. It will be going on here. So all the delegates, please come to Annapurna Auditorium after Dr. K. Shaktipandi sir's presentation. Thank you. I once again repeat, 11:30 a.m. to 12 p.m. session will be handled by Dr. J. Madhavan sir, and that session will be going on in Annapurna Auditorium. So after Dr. K. Shaktipandi sir's presentation, I request all the delegates to come back to the auditorium. Thank you. Check. We'll be proceeding with the first technical session of this day. This session will be handled by Professor Dr. S. Anandan sir, Department of Chemistry, National Institute of Technology, Trichy. Sir will be dealing with the topic nanocarbons, graphene, etc. as a promising next generation energy storage material.
This session will be chaired by Professor Dr. Reena Rachel John Ma'am, Vice Principal Research, Vinayaka Mission, Shankaracharya Dental College, Salem. Over to you, Ma'am.
Thank you. Good morning, all. It is my privilege to introduce the speaker of today, Dr. Samandam Anandan, who is a professor of Nanomaterials and Solar Energy Conversion Lab, National Institute of Technology, Trichy. He is graduated from the University of Madras in 1993 and a doctoral degree from the University of Madras in 2002. He went on to do his postdoctoral fellow in the Department of Chemistry from Chungam National University, Korea in 2002-2003. He is at present the professor of the Department of Chemistry in the National Institute of Technology, Trichy. He has been a lecturer and associate professor at the same institute. He's also been the pool scientist of the Central Electrochemical Research Institute, Chennai Unit, Tharamani, CSIR, from May 2005 to July 2006. He's been awarded a lot of honors, among which are the Department of Science and Technology Award for participation in the meeting of Nobel laureates and students in chemistry for the year 2006 that was held at Lindau, Germany from June 25th to June 30th of 2006. He's also been awarded the Royal Academy of London, who selected Dr. Anandan, the eminent scientists of India, for participation in the meeting of engineering challenges of deployment of new solar energy capacity in India, held at Royal Academy of Engineering, London. He is also an editorial board member for International Journal of Applied Biology and Pharmaceutical Technology. He's been awarded the Hiyoshi Young Leaf Award in 2009, and he's also been awarded the Best Teacher Awardee by the National Institute of Technology in 2010. He's also been awarded the Best Teacher Awardee in 2011 by the Chemical Research Society of India. He's also been awarded the Hiyoshi Environmental Award in 2014 for his outstanding contribution to applied study for environmental conservation and protection. He's projects that have been completed worth 15 crores, and he has 4 projects that are ongoing. He's also dealing with international projects with countries like Australia, Spain, Taiwan, and Russia. He has more than 355 research publications in international journals, 23 book chapters, 2 patents, and he has trained 26 PhD students. 4 are under his training. His research area is sonochemical synthesis of nanoparticles towards energy storage applications, electrochemical and fluorescence sensors, dye-sensitized solar cells, organic polymer solar cells, synthesis and characterization of nano-photocatalysts for the study of decomposition of inorganic and organic pollutants, generation of hydrogen fuel using semiconductor nanoparticles. What a wonderful CV that we have. We understand who you are, sir, who is going to talk to us for the next half an hour. Over to you, Dr. Anandan.
Thank you, ma'am, for the kind introduction. Also, I thank the organizers of Vinayaka Mission for inviting me to deliver a lecture in front of the young birds of this institute. Okay. So, good morning to all. My topic will be nanocarbon or graphene as a promising energy storage material. So, why this carbon? You know, carbon is nothing but any wood you can burn, you get a carbon. But we are interested in nanocarbon, okay, and that too graphene and carbon nanotubes. So what is graphene? Graphene is nothing but a mat-like structure. It's nothing but a mat. When you roll down the mat, we get a carbon nanotube. So when mat's properties are different, when it's carbon nanotube, its properties are different. So we want to see the properties. Okay. So first will be, people will make the mat and make a carbon nanotube from graphene. That's an interesting way. But interesting way is making carbon nanotube from graphene is already old. But what we want to do, broke the carbon nanotube, and then we want to make once again nano sheets, then properties how it looks. That's our interesting way we want to think in this lecture. Okay. So before going to this, what is meant by supercapacitor and where we are in energy system. So okay, we can see energy will be different types, okay, starting from your tidal energy or solar energy, etc. So we can see this will be mostly coal. People are using coal as the main energy in the world today, 40%. So still our renewable energy is very, very less actually, okay. We can say our renewables are less than 0.5%. So we want to improve the renewable energy to get a good fuel in day-to-day life and cheaper one. Among the renewable energy, what we want, we are not storing energy. We are just creating energy, but we are not storing energy. To create energy or store, we want to go to supercapacitors, which is a very important thing actually, okay. So we want to make a supercapacitor to store this way actually. So how to store this supercapacitor? We have many things are there. So in this form, batteries, the previous lecture given by the Thailand professor, so that we don't want to move that, we want to only store energy using a supercapacitor. So what is supercapacitor? So supercapacitors are unique electrical storage devices that can store much more energy than conventional capacitors, offer high power density than batteries. Okay, for example, battery we can start, it takes much time. but supercapacitor can store energy and start in few seconds. That's advantage of supercapacitor compared to batteries. So two primary things will be there for capacitor and supercapacitor. Capacitor will be energy density is low and power density is more. Battery will be opposite. Supercapacitor will match these two things and give a advantage. That's advantage of a supercapacitor compared to the batteries and normal capacitors. Okay. So supercapacitors will consist of electrode, electrolyte, separator and current collector, so that we don't want to go inside. Among these electrode or electrolyte, people use mostly carbon. Okay, carbon is the only material we use, so we want to focus on carbon directly and we can see what happens, the carbon can be changed. Okay. So what is meant by nano? Nano will be, we can see 0 to 100 nanometer. That will be called nanoparticle. See, we simply say nano will be different types, 0 dimension, 1 dimension, 2 dimension and bulk material, that's called 3 dimension. A bulk material is a bigger structure, that's called 3 dimension material. 2 dimension will be we called as a sheets, okay, graphene sheets or borofin sheets. Mostly the layer structures are called as a 2 dimension material. And 1 dimension will be your nano rods, pillars, wires will be 1 dimension, and 0 dimension will be the particles. So anything you broke into smaller one, we call nanoparticles, okay. So nanoparticles, nanorods and layer structure, we want to only go to 2D structure, okay. 2D is most important because 2D structure will be layer by layer structure will be there, which can give intercalations of particles over there and give a efficient properties because of more surface area. So we want to focus on 2D material, particularly graphene, carbon nanotube, etc. Okay. So I told carbon nanotube is a very innovative series. Already it is 20 years old. People are mostly not interested in day-to-day life now. So carbon nanotube used as a supercapacitor, you can see a very broad window, minus 0.1 to plus 0.1. Very broad window we can see. And no any oxidation reduction potentials. Very important here for supercapacitor. It should not show any oxidation reduction potential. So carbon nanotube, we can see a very broad window, this one. If we go to the carbon nanotube to graphene also shows similar properties actually. So very broad window actually, okay. So what happened now? So we can see this compound, graphene and carbon nanotubes are very good charge storage density. You can see here this one, very good charge density in this point, okay. So that's why the people say carbon nanotube is best material among the carbon, okay, any carbon forms. So you can see graphene. Graphene is a sheet structure, okay. We can see graphene can go from 0 to 4. We can see here in this area. Previously I told minus 1 to plus 1 with carbon nanotube goes. We can see this will go for very big window in electrochemical, okay, 0 to 4. So that is a very important property of graphene nanostructures. So graphene nanosheets have great window 0 to 4. Carbon nanotube is minus 1 to plus 1. So we see graphene has more sheet-like structures, good properties. So now what we happen, we want to go to unzipping of multi-wall carbon nanotube. So what we do, I told previously people take graphene and they make a carbon nanotubes. So making carbon nanotubes is very important work. But now we want to break. What we do simply, if you sit in the chair, creation of chair is one important way, but after your creation, what you sit in the chair, you've broken the chair. What layer by layer you've broken. Okay, you put your fingers inside and broken. Same thing here, you take the carbon nanotube, we want to unzip. You can see here, we want to unzip the carbon nanotubes. This is the place where you can insert your finger and broke the carbon nanotube into a sheet structure. Okay, so just your bag, insert your bag, zip and unzip. So we call this the unzipping of your carbon nanotube. So we take the carbon nanotube and unzip the carbon nanotube to make a sheet. So sheet may be very easy to make carbon nanotube. We can roll the mat, we can make a carbon nanotube. But now, broke the carbon nanotube by unzipping. That's very tough. Lot of processes are there by wet chemical process or dry chemical process or using an ultrasound we can use. So these processes are taking much efforts. We want to go very simple method to make a unzipping of carbon nanotube. You can see we can have lot of methods are there. So they take the carbon nanotubes in the center and they unzip to form a carbon nanotube structure into unzip to sheet morphology or CGN curved graphene nanosheets or unzip multi-organ into sheet morphology. So they do many processes, many methods are available, but we use simple method ultrasound to make them. What is ultrasound? is only sound energy. We apply sound energy and make a particle to open the zip, unzip your carbon nanotube. So what is ultrasound? Which human cannot hear. Okay, that ultrasound waves we can use sound energy and we can unzip the compound. So ultrasound waves people can hear will be only 20 kilohertz. Below 20 kilohertz will be only infrared sound waves. Only the grasshopper can make such noise. About 20 kilohertz will be called 200 megahertz. We can know this is in hospital. They can scan your body, okay? They scan your body with the high power ultrasound 200 megahertz. So we don't want high power, we don't want low power. We use only 20 kilohertz ultrasound waves to unzip the carbon nanotube into graphene nanosheets. We want to do this process. So you can say this is the multi-wall carbon nanotube, which is a carbon-carbon double bond structure. That means it's the sp2 hybridized carbon will be there. Okay? So what we do, first we can modify it. Okay, first we can modify it, we can functionalize this compound. So carbon nanotube has no functional group actually. We functionalize to form a OH group, COH group or ester group, carboxy or hydroxy or ester group we can modify first by Ammas method. Once you modify the compound, then you apply ultrasound in presence of catalyst tin. Okay, in presence of catalyst tin oxide, we take a tin chloride. We take tin chloride is called Lewis catalyst. Lewis catalyst can break the bond. You know, bond formation has 2 electrons. So when you break the bond, one electron go this side, electron go outside. That's called bond breaking actually. We call Lewis catalyst can unzip. So this bond breaking tin chloride will apply. It can break the bond. You can see double bonds are here. It can break the bond here, functional carbon, and all the tin will occupy in the structure, and one by layer will be formed. That's the advantage of your compound. So we can see this is called unzipping of your multi-wall carbon nanotube using ultrasound method using a Lewis catalyst tin chloride. So when tin chloride is oxidized, it forms tin oxide. The tin oxide will be occupying the sheet structure as a particle. So we have a layer structure and also we have particles of tin particles are there in this. These 2 important compounds will give an enormous power storage capacity we can see. So we can take multi-wall carbon nanotube, apply 1 hour stirring in ice bath and apply oxidation KMnO4 to get your compound, and finally we can get your functionalist carbon nanotube. After that, apply your ultrasound, we get your unzipped multi-wall carbon nanotube with tin oxide on the surface. This is the preparation method of your compound. So we have to characterize. So very important characterization will be XRD. You can see here, multi-wall carbon nanotube will give a peak here at 20.25 Hz, 002 peak actually will be noticed. When you functionalize the compound, that peak will be disappeared. That means multi-wall carbon nanotube will become sheet morphology, that's why oxidized. Once you oxidize and then apply tin chloride, we get new peaks of form. So it shows that tin will be on the surface of your multi-wall carbon nanotube. So that's the important section. But we go to the FTIR, because of the epoxy group or hydroxy group, we can notice the more functional groups are there in the compound. That's noticed in the unzipped multi-wall carbon nanotube. This is a basic structure. UVB is also a very basic structure. You can see compound multi-wall carbon nanotube. The carbon, no absorbance. Okay, carbon is a black in color, no absorbance. When you functionalize, it shows some absorbance peak. With tin oxide, it shows some peak. Therefore, we can say that some morphology will be changed. So TGI is keep actually. Just go to your Raman. Very important here. Raman, we are proud. We are the Indian Raman is from India. He is the one give lot of structures. You can see here a carbon-carbon double bond will be like this. In the carbon-carbon double bond will be there. A D band will be always shorter and G band will be more. So the carbon-carbon double bond is broken, then we notice your D bond will be increased and G bond will be decreased. So this gives that your carbon becomes sp2 to sp3 hybridized. So we can see multi-wall carbon nanotube will be D band is more. That means sp2 carbon is there. But when you get your sheet, the D band structure will be increased. That shows the compound will be sp3. That means carbon-carbon bond is broken actually. So we go to the morphology. You can see carbon nanotube will be a tube-like structure. When you functionalize, tube will be almost small together. When you apply tin chloride, it becomes sheet. All the carbon nanotube is open to become a sheet. So we can see TEM image, then you can conclude. So carbon nanotube will be structure will be there in the first one. Okay. So when you open the sheet, we can see sheet structure. We can see the compound will be here. All the carbon nanotube will be broken and get a sheet formology. So this shows that your sp2 bond is broken to get your sp3 bond. That's a very important here. We can get this compound here. Okay, so we have to say, sir, carbon nanotube you can broken, you confirmed. So no one accept because carbon nanotube is long tube carbon bonds are there. So what we take a small organic molecule. Okay, that's called your 1-pyrene carboxylate. Because we know in the carbon nanotube function is COH group is there, we take COH group. Carbon-carbon double bond, small carbon is called pyrene compound. We apply similarly to a SN tin chloride. We see same morphology. So we notice by same image, we can see here, this is the pyrene carboxylate, which on apply sound sheet morphology noticed. Okay, you can ask here, sir, how much time taken to open structure? First, we can apply ultrasound for 30 minutes and we see the tube will be there. After 1 hour also tube is there. After 3 hours, the tube will be entirely broken and we see that it become a sheet structure. That's the advantage of your ultrasound. Okay. Once you make the ultrasound, then we want to give energy storage capacity. We want to make a supercapacitor. Okay, we want to make store energy. So what we make, we take the material, that's our unzipped multiple carbon nanotube, it's called prepared material, on which we can use the Vulcan carbon some amount and PVDF piezoelectric material, and then we make electrode of 1 square centimeter. Once we make the electrode doping, and then we connect to a potential stat, and we want to measure the working electrode capacity, or we can be able to make a supercapacitor. So we told carbon nanotube is from -1 to +1, and graphene will be 0 to 4. So we do the potentiometric graph -1 to plus area 0.8, or we can change electrolyte. We use 2 types of electrolyte. One is called 1 molar sodium sulfate, other is called 6 molar KOH. So with 1 molar sodium sulfate, we can see the window 0.8, very broad window is there. Similarly for KOH also very broad window. So which shows that compound has no oxidation and reduction potentials, which concludes that the material has a high storage capacity. We do with different potentials varying actually from 20 to 60 millivolt. We notice the same graph is noticed, and you can see the graph will be triangular form. You can see the inside area, the form, okay, rectangle form. The rectangle form will shows that compound is stable for a longer period. That's the conclusion we can get from our system actually. So based on that, we have to calculate your chemical surface area measurement. The surface area measurement will be more high for this compound. So we conclude the material has good capacity for energy storage capacity purpose. So very important here, when you use a capacitor, it should be charging and discharging. So how much will be charging, how much will be discharging current. So we can notice here immediately charging and discharging will be there. We can see the graph will be somewhat bent and straight line. This is called IR drop. The IR drop will be there. But when you go for longer cycles, 24,000 cycles, the IR drop will be reduced. We get a peak, perfect peak will be there. This concludes the material has a high storage capacity can be obtained. So we do a sample. We conclude with the multiple carbon nanotube. We do in our laboratory only 14 Faraday per gram storage capacity, whereas the functionalized one is 110. Whereas the open structure, that's sheet structure, we unzip carbon nanotube with 350 Faraday per gram. You can see 14, 110 and 350. How much enormous increase in the supercapacitor storage capacity. This concludes that this material is a very good high storage capacity can be noticed. That's the advantage of your unzipped carbon nanotube. Is better than the multiple carbon nanotube and better than the graphene. That's we conclude, we have a conclusion arrived. Similarly with 6 molar KOH, we also get 8, 38 and 48. So which is better, 6 molar or 1 molar sodium sulfate? So this is higher. So we think that 1 molar sodium sulfate will be pH neutral 7, whereas this will be pH 9. So pH 7 is better, therefore sodium sulfate is better compared to your KOH solution electrolyte. So we do the impedance and we can conclude the electrode will be how the resistance will be maintained, charging and discharging, or how the kickstart, or we can give a power density, etc. We maintain. We find this compound will be better than a capacitor and the battery. That's the conclusion we come from the electrochemical impedance spectroscopy. So we conclude from this one. So we used your compound with tin oxide and carbon, compare with tin oxide carbon, multi-wall carbon, and tin oxide CNT, tin oxide and RGO, tin oxide and single wall carbon nanotube. Ours is unzipped. This is all ready-made available. We've broken the compound carbon nanotube and fine. We get a higher current. You can see that we get a higher current from everyone. So our system is better than any other one. So in this way, what we conclude, we take a tin chloride and then make a carbon nanotube. Okay. So what is tin chloride? It's called as a Lewis catalyst. So we think that to break the carbon nanotube, tin chloride is very important. So tin chloride is a Lewis catalyst. So this is maybe, tin is maybe somewhat expensive for us. We want to make a cheaper Lewis catalyst. So we want to move to the next study. Okay, this is next study. We want to use a titanium chloride. Titanium chloride may be cheaper Lewis catalyst to make a energy storage material. So we take carbon nanotube, multiple carbon nanotube, functionalize it, and then instead of tin chloride, we use titanium chloride. We use titanium chloride, and we get a sheet structure very easily. You can see here, this is the one we do. So instead of, we want to confirm the Lewis catalyst is the only one which broke the bond. It's unzipping, cut the carbon nanotube, or the ultrasound. So we think that tin chloride, instead of tin chloride, titanium chloride also do. That means Lewis catalyst will play a role in addition to ultrasound. That's the conclusion we get from our system. So we can use your titanium chloride, and I just keep going. I just show you Raman. You can see Raman. So tin chloride is Raman will be same height. The titanium chloride Raman will be D band is higher. This shows that titanium chloride cut the structure very fast compared to tin chloride. That's the conclusion we get from the first point. Second point, morphology. Your carbon nanotube will be morphology very easily shown, the broad cutting actually. So that's a titanium chloride is better than tin chloride. Okay. So cyclic stability, we make electrode, we find cyclic stability of the electrode almost same. Okay. So in two variations, KOH and sodium sulfate, everything actually. And we want to optimize this one. Which one is better actually we can find. So but we can see here, this structure give a value 190 Faraday per gram, but we get 351 directly. That's a difference. So even though you cut the material faster, the storage capacity is very less for this compound in Na2SO4. But in the case of your KOH, this shows a better one. In the case of sodium sulfate is better in the first case. In the case of second case, KOH is better actually. It gives 475 Faraday per gram. So we feel that with the KOH electrode, it shows a higher Faraday per gram in this concept. Okay, that's our conclusion we can get from this system. In this way, our system will be better. We can see in the case of a compound, we get your compound will be 475 Faraday per gram is better than your previous system. That's the conclusion we can arrive from this point of view. Okay. So with this, I want to come to a conclusion of this work. So unzip, we can see creating multiple carbon nanotube is very tough, but we can cut the multiple carbon nanotube to unzip multiple carbon nanotube, which can give a better value, we can notice. So this unzipped multiple carbon nanotube is better material compared to the multiple carbon nanotube as well as graphene. So that's the conclusion we can give from this point of view in this study. Okay. So if you want to say something more, time is there or can continue? Okay. So some more research we can see, people say, sir, you compared graphene. Yeah, we compared also graphene. So we purchase graphene directly and we add manganese oxide, and we can see structure will be more improved. Okay, that is the one, I just keep the one. So we take the graphene oxide and we load manganese oxide and we get the manganese oxide doping on the graphene sheet. So that also shows a better capacity. I just keep this one because you can see these are graphene nano sheets on which we can see manganese will be doped. So this also give a better, instead of your unzipped one, we take a graphene nano sheets and we find manganese oxide will be better material for supercapacitor value. Okay. Okay, I just keep this one. AFM also shows the sheet structure. Okay. So what happened now? People can say one-dimensional material is better, or two-dimensional material is better, or three-dimensional material. So we can use almost two-dimensional material. But we can also choose three-dimensional material. We don't want graphene, we don't want manganese carbon nanotube. What we do, we take instead of graphene, we take a boron nitrate. Boron nitrate is also a sheet-like structure. So what we do, we take boron nitrate coupled with graphene nitrate and nickel nitrate. When we coupled all the things, we expect sheet structure, but we get something called a flower-like structure that's called marigold flower-like structure. It's not a two-dimensional material, now it's a three-dimensional material. So when RGO mixed with boron nitrate sheet, it gives a three-dimensional material. It's a marigold flower-like material. You can see here, I can show the structure. Okay, this is the structure. This is a semi-image, looks like this image. See, this is a marigold, almost same structure we can get from our system. When you prepare your graphene nanosheets and boron nitrate nanosheets coupled together, we don't get the sheet structure, we get a different morphology, marigold flower. I can show the structure once again, semi-image. Yeah. See, graphene will be sheet structure, boron nitrate also sheet structure. When you couple together, it form a marigold structure. You can see the structure will be like a flower. So that is the morphology. Morphology now, even though sheet morphology is maintained, it gives a marigold flower, and this compound has three-dimensional material, and this compound shows very good activity. I can show here, CV, just keep this one, final value only. Because of shortage of time, I can give a final value. We can get a current of 118 watt per kilogram current density actually, in this case of RGO, boron nitrate and nucleic oxide. So what is the conclusion we can get actually? Among the three materials, which is better, we can see unzipped multivalent carbon nanotube with tin oxide, unzipped multivalent TaO2, RGO, boron nitrate sheet. But unzipped multivalent TaO2 is better material compared to the other two. So two-dimensional materials are better than your bulk material. That's the conclusion we can arrive from this work. Okay. So I thank the organizers. This is the value we can get. Comparison purposes, we put here what is the value, energy density and power density. Energy density will be TaO2 will be more, 280, 14 compared to other two. So we can use this material for making a wearable supercapacitors. We can run the transportation in small cars, etc. This is the application supercapacitor we can do in our laboratory. So how much current, we can just calculating, and we are measuring this one application in our laboratory, just started actually. I thank the organizers for giving opportunity to share our work in the Vinayaka Mission University forum actually. Thank you one and all for kind introduction.
Thank you, Dr. Anandam, for that wonderful presentation of yours, helping us to understand the use of nanocomposites in superconductor applications. Are there any questions from the audience, from the young ones there? Yes, I have a hand there. Please, you can use this mic if you want.
Yeah.
Sir, thank you for your wonderful session at first. Sir, my doubt is, like, I have seen usage of carbon nanomaterials for energy storage and supercapacitors. And recently, I have seen few articles mentioning about usage of nanosilicon particles, like silicon nanowires. So what is your opinion on it, on usage of silicon nanowires or nanosilicon particles?
Yeah, the silicon nanowires or silicon nanoparticles we have used actually. See, when you compare this one-dimensional material, it's called one-dimensional material, you compare to zero is better actually. But you go to two-dimensional material, surface areas get enhanced particle. So enhancement of surface area gives a lot of properties. So that's the way we are focusing on more surface area properties. For example, you know, small particle surface area is less.
Yeah.
If your particle surface area is more, it will give an enormous current actually. That's why we are focusing on
that. Is why you are focusing on 2D structures and 3D structures mostly. Yeah. Thank you, sir.
Thank you.
Question, anybody else? Yeah, there's another question there behind. Yes.
Thank you, sir, for your wonderful informative talk. My question is regarding your Lewis acid, which used in tin chloride as well as the titanium tetrachloride. But these two compounds, particularly tin chloride, is toxic and practical difficulty will be there. Instead of that, did you try aluminum trichloride, or this would make the practical, in terms of synthesis wise, it will be easy.
Yes. Good. Thanks for a good idea actually. Actually, we started with tin chloride. We have used a catalyst a small amount. We don't use grams. We use only few milligrams only, first reason. That's why we, instead of tin chloride, we moved to titanium chloride, because titanium chloride is a pigment used in all the paint industries, which is not toxic for us actually. We tried aluminum chloride, but what happened, we don't get more cutting of the properties. The properties will be still maintained, the tube will be maintained. So that's the reason we are not shown any data. But aluminum chloride is a good catalyst, Lewis catalyst. We tried, but we don't succeed in getting a good enormous value. Okay, thank you.
Okay, thank you, sir.
Thank you. There's another question behind. Behind, please. Sir, behind.
Sir, good morning, sir.
Yeah.
Can you tell the self property of this self-discharge property in which you have sent it, sir?
Self-discharge property. We have done the galvanostatic charge discharge properties actually. So when you make this electrode, 2 electrodes, we can make as a galvanostatic charge discharge properties. You can see the graph actually, just show you graph actually here. One system, I'll show you graph. Okay. So if you take a galvanostatic charge discharge properties, so in the electrode, if you use a supercapacitor 1, generally we take the compound and do the potentials. You can see in the graph where the current will go. We want to make very broad graph, and also the charge discharge capacity should be maintained almost same. Even 22,000 cycles or 10,000 cycles should maintain same. Then it has a good we can say good retention capacity, and it can hold for longer purpose. So we did this one for more than 24,000 cycles actually. It maintains same value, and we find this is a good capacity value actually.
So I'm asking about the self-discharge property of the material.
Self-discharge property. That's why we can see in this case, this is your way. Charging is here, and you cut the time of discharging. Understand that? So this is a charging graph, this is discharging graph. Okay? That is the important point. So you can charging and discharging we do consecutively, we can get your value maintained. That's the point. Okay?
Thank you, sir. Any other questions? So since we don't have any more questions, thank you, sir, for presenting your wonderful work. It's an inspiration for all of us sitting here to work on our projects. Thank you, sir.
Thank you.
Check. Thank you so much, sir, for your words of wisdom and sharing your knowledge with us. Thank you, sir. I now request Professor Dr. Reena Rachel John, ma'am, to felicitate our speaker, Professor Dr. Anandan, sir. Thank you, ma'am and sir. I kindly request Dr. Surya Narayanan, sir, Deputy Director Research, VMRF DU, to felicitate Professor Dr. Reena Rachel John, ma'am. Thank you, sir. Thank you, ma'am. We now move to the next technical session for the day. I request Dr. M. Asha Johnsi, ma'am, Associate Professor, B.S. Abdur Rahman Crescent Institute of Science and Technology, Chennai, to proceed with her presentation. The topic will be multifarious applications of carbonaceous materials in biotechnology. This session will be chaired by Professor Dr. N. Palanisamy, sir, Department of Chemistry, VIT University, Vellore. Over to you, sir.
Okay. Good morning, all present here. I would like to thank the organizing committee for the opportunity to chair this session. Okay, now I welcome Dr. Asha Johnsi, ma'am. Dr. M. Asha Johnsi has received her PhD from School of Chemistry, Bharatidasan University, Tamil Nadu, India. She moved to General Electronics India, Bangalore, for her postdoctoral consultant and worked on the project phosphorylated siloxane as a flame retardant and nanocryo as a coating material. And she is a well-versed research area of photophysics, photochemistry of nanomaterials and quantum dot for solar cell applications. Currently, she is working as an associate professor in the Department of Chemistry of Crescent Institute and handling BTech and postgraduate courses for more than 12 years. She has served as a mentor and supervisor for 20 postgraduates and 2 PhD researchers. She has an excellent contribution to science and she has a 47 research publication and H index of 19. Till date, she has completed 2 funded projects such as a SERB startup and SERB Teachers Associateship for Research Excellence with the collaboration with the Indian Institute of Technology, Madras, Chennai. She served as a mentor for 2 student project scheme through Tamil Nadu State Council for Science and Technology. Her contribution to Crescent Institute and recognized and were awarded Best Young Faculty 2019 and Best Faculty Female 2021. Recently, she has been selected Isaac Nasi INSA Summer Research Fellowship by the Science Academic to work at CSR Sikri Karikudi for the period of 2 months. She is serving as a review for several reputed journals. Her research interests include solar cell fabrication, fluorescent-based chemo and biosensor, nanomaterial and quantum dots for energy-related applications, and waste to value-added product conversion of sustainable development. With this introduction, I invite Dr. M. Asa Johnsi for the topic of multi-fabrication applications of carbonaceous materials in nanobiotechnology. The floor is yours, ma'am.
Thank you, sir. Good morning to one and all. Thank you, Chairman, for the nice introduction. Before starting the talk, I would like to thank the organizers of INEEBA-2023, especially Dr. Anbaragan sir, who is my super senior. I would like to thank my research supervisor, Dr. Ranganathan, who is sitting over here, and Professor Anandan, who is my doctor committee member during my PhD tenure. So let us move on to today's talk. Multifarious applications of carbonaceous materials in nanobiotechnology. During my PhD tenure, I was worked in the quantum dots material, chalcogenide based quantum dots. After joining in Crescent, I moved to the carbon-based nanomaterials. So this is Crescent. Crescent is located in Vandalur, Chennai. It's famous for its green and clean campus. Every year we are receiving the awards for maintaining the green campus. And this is the view of Crescent from quarters. We are staying in the Crescent campus, and this is the clock tower. And Crescent is famous for biodiversity also. This is an example. We have a variety of species inside our campus. And this is our department details. We are 17 faculty members with all our doctorates, and they are doing research in a different field. Dr. S.K. Rani, first year coordinator, and Dr. N. Hajna Bibi, HOD of chemistry, and other faculty details you can go get in the Crescent website. And this is a few works we are doing in our research group. From 2013 onwards, we are working in the field of carbon-based nanomaterials, especially fluorescent carbon nanodots for energy, environment, and biomedical application. In the last INEEBA 2022, I have presented the carbon nanomaterials for energy conversion and storage. So mostly we are working on the sustainable development goals such as affordable and clean energy, good health and well-being, clean water and sanitation, and climate action. So objectives of today's presentation. Let us discuss about the carbonaceous nanomaterial. The earlier speaker, Dr. Anandan sir, has talked about the one-dimensional material carbon nano tubes. So I would like to discuss the zero-dimensional carbon-based nanomaterial, the fluorescent carbon dots especially. So the conversion of biomass into fluorescent carbon dots and its application in biosensing, bioimaging, and drug carrier. So collectively it is known as thermastic agents. So the introduction about the carbon-based nanomaterials already Professor Anand has given the talk. The zero-dimensional fluorines, one-dimensional tubes, two-dimensional sheets and layers, and three-dimensional bulk graphite materials. Basically, it's a honeycomb structure. So why nanocarbon? So every people are nowadays, in the past 1 decade, many people, I would say, they start doing the carbon-based work. That is due to its abundance is high, it's chemically inert, and its toxicity is less, and it's having negligible photo bleaching, which is nothing but in presence of the sun energy, it will not undergo degradation. And it is facile and economical for the large scale preparation. And the biomass, whichever the plant materials or leaf materials, whatever, everything is consist of rich carbon percentage, so that you can convert into carbon-based nanomaterials easily. So this is a structure of carbon dots which contains the graphitic sheets at the center core, and the edges, it is having amorphous functional moieties like epoxide, hydroxyl, carbonyl, and carboxyl functional moieties. And so photovoltaic and photocatalytic applications in the last INEEBA itself I have covered. Today we are going to discuss about the sensors and nanomedicines. So the top figures which shows the biomass so far we have converted into fluorescent based carbon nanomaterials, which are already published from our own research group. So carbon nanomaterials we can prepare from both top down as well as the bottom up approaches, like hydrothermal, microwave, electrochemical, acid oxidation, and direct pyrolysis also. So if you search in the literature, you can see the n number of articles which are relevant to the biomass conversion. So we are focusing in the fluorescent based carbon nanodots, like graphene quantum dots, carbon quantum dots, and carbon nanodots. So graphene quantum dots are a single 1 atomic layer thickness of dot material, zero dimensional. Carbon quantum dots are few layers of the graphene are stacked together, and carbon nanodots are the amorphous structured material. The origin of the fluorescence are two types. One is from the band gap transition due to the conjugated pi domains of the carbon-carbon double bond, and the other one is the fluorescence from the surface defects, which are due to the functional moieties present in the carbon surface. So biosensor, a device which consists of the receptor, which is depends on the size and shape of the receptor. It can able to detect the specific analyte, and there will be a transducer and the display. This is the setup of the biosensor. So biosensor is having the wide range of applications in this many fields, in soil quality monitoring, water analysis, food monitoring, pathogen disease detections and all. That's why it's gaining much importance. So these are the different methods of sensing are available: physioelectronic, electrochemical, optoelectronic, and calorimetric. We are focusing on this optoelectronic fluorescent based sensing. So the green synthesis of bio-derived carbon nanocubes and its utility in sensing of antibiotics. So this particular tree is a mahua tree, which is located in our Crescent campus itself. So when we are searching the literature survey, most of the carbon-based nanomaterials are rich in sugar moieties, which can be easily converted into carbon nanodots. So this particular flower, mahua flower, which is around 58% of reduced sugars are present. So why don't we convert this sugar moiety into fluorescent carbon dots? That is what the ultimate aim. We have followed the hydrothermal methodology for the conversion. So the prepared material is characterized using the microscopic, electron microscopic, as well as the spectroscopic techniques, high resolution transmission electron microscopy and scanning electron microscopy, which exhibit the cubical structure, and the particle size is around 4 to 5 nanometer average particle size from the histogram plot. And FTIR and Raman analysis for the specific for the functional group confirmation, as well as the D band and G band for the carbon sp2 and sp3 hybridization present in the carbon nanomaterial. And this is XPS analysis for the surface bonding nature, O1s and C1s. The top one is the survey spectrum, and the bottom two are the deconvoluted spectrums, which indicates the carbon is bonded with the carbon-carbon, carbon-oxygen, and COC. The different variety of functional moieties exist on the surface of carbon nanomaterial, which is responsible for the water solubility as well as the fluorescent behavior of the carbon material. So this is the photophysical studies. The absorption and excitation dependent emission phenomena, which is the unique property of the carbon dots. When you are changing the excitation wavelength, the emission behavior is varying. That is due to the surface defects as well as the functional moieties present. This is a decay lifetime analysis, the 3.47 nanoseconds of the average lifetime. So we have used the prepared fluorescent carbon nanomaterial for the sensing of antibiotics. So what is the importance of sensing the antibiotics? Antibiotics, we are using it for the bacterial, to reduce the bacterial infections. The two antibiotics such as nitrofurazone and sulfamethoxazole, these two, the first one is used for the skin disease and the second one is highly useful in urinary tract infections. But once after usage, these are going to leach out into the soil and the aquatic system, which can be increase the toxicity level through the biomagnification, which is nothing but the increase in concentration of the toxicity through the via the food chain. So it is necessary to sense or detect the limit of this antibiotics present in the water resources. So here in this particular work, we have compared both electrochemical as well as the fluorescent based sensing methodology for the detection of this nitrofurazone as well as the sulfamethoxazole. So these are the electrochemical based sensing of nitrofurazone, and the limit of detection is in the range of 80 micromolar. And this is through the chronoamperometry, the sulfamethoxazole detection in the range of 13 micromolar LOD is achieved. And this is the absorption studies before doing the fluorescent based sensing. We observed that in absorption studies there is not much change, only the rise in the optical density of the carbon dots in presence of the nitrofurazone. There is no complex formation, but in the fluorescence you could see there is a decrease in the fluorescence intensity, which indicates fluorescence quenching is occurred. Through the quenching, there will be interaction between the nitrofurazone and the carbon based nanomaterial. The quenching is due to the static mechanism that is confirmed through the lifetime analysis. So in this particular work, we have successfully converted the sugar containing biomass into carbon nanomaterial. That carbon nanomaterial was successfully used as a sensing agent for antibiotics. And this is the second work, the waste to value added product conversion. The biomass, the dried rose flowers, that biomass we have successfully converted into fluorescent carbon nanodots through the hydrothermal methodology. These are the steps involved in the conversion of biomass into fluorescent dots. So this is the proposed mechanism for the conversion of the biomass into fluorescent carbon dots. Here this particular work is, we would like to use the carbon nanomaterial as a nano carrier for the drug, which is actually the thymol, which can be used as an anti-arthritics agent. So this is the center one is the structure of the thymol. So in general, for the rheumatic arthritis disease, people are using steroidal based drugs, which may cause the side effects. So in order to avoid these side effects, we want to use a non-steroidal based drugs. So for example, the thymol. Instead of injecting the thymol alone, why don't we use the carbon material as the carrier to reduce the dosage level of the thymol? That is the ultimate aim of this work. So these are the characterization part. So in vivo studies, so the control rods, this is actually around 22 to 23 days of process. This particular work is done with the help of Dr. Shivasudha from Bardhasan University, and the student involved in the project is Mr. Salem, the MTech biotechnology student, who did his project work in this particular work. So the 6 group of the Vista rats are collected and they have maintained for 7 days. After that, they have injected the rheumatic arthritic agent like FCA. That FCA induced rats are maintained properly as per the animal studies ethics. And the control here they have used is Brufen, and they have injected the carbon dots alone and thymol alone and carbon dots and thymol conjugate. So in order to check the efficiency. And so after injection, they have sacrificed the animal species. They have checked the body weight variation during the treatment process. This agent, whatever they have induced into the rat paw, that is causing the inflammation as well as the bone level decrease. The A is the control and B1 is the disease induced picture, and C is the individual carbon darts, the individual thymol, and the last one F is the combination of the thymol carbon dart conjugate. So the related hematological parameters during the course of the treatment, it is thoroughly checked, like hemoglobin, red blood cells level, white blood cells level, plate cells and all. The animal has been undergone the proper studies and analysis. And they have used the radiological ultrasonographic images to check the inflammation studies, and in order to study the bone effect, they have used the X-ray imaging. So it is observed that in the F picture, the thymol and the carbon nanomaterial along together, which improves which will act as an anti-rheumatic arthritis agent. So if you use only thymol as the drug, that needs a 25 milligram per kg body weight of the animal species for the curing of the disease. But if you are using carbon darts along with the thymol conjugation, the drug dosage is only 5 milligram per kg of the body weight of the animal species. That indicates 5 times the dosage can be reduced if you are using carbon darts as a carrier for the drug. So, and the third one is the fluorescent based carbon nanomaterials, which can be used for bioimaging studies, in vitro studies also. For this bioimaging and as well as the nano carrier, and for the drug delivery therapy. So the prepared carbon nano dots can be used as a therapeutic agents. That is what the ultimate conclusion of the present work. So these are the work recently we have completed. One more waste to value-added product conversion. We have taken the azo dyes, which are the dye effluent from the industrial effluent, which we have generally people used to degrade the dye molecule to reduce the toxicity level, but we wanted to convert that waste water itself to convert it into a useful product. So we have taken initially the gongo red dye that we have converted into fluorescent carbon darts, which was used for the sensing, ferritin ion sensing. And for one more biomedical application, at present we are working in the bandage, wound healing bandage fabrication by using the Tridax precumbens, which is a well-known traditional medicinal plant available everywhere in India and in Asia. So that plant extract we have converted into carbon-based nanomaterial. The same time, the same extract can be used as a wound healing agent. So we have fabricated the wound healing bandage, which is under testing for the submission of the wound healing studies in animal studies. So this is actually a Tamil Nadu government funded project. So these are our collaborators, international level and national collaborators. So I would like to thank the INEEBA organizers as well as my funding agencies, SCRB for the funding, and Tamil Nadu State Government for Science and Technology for student scheme. Consequent 2 years we are getting the funding from Tamil Nadu State Government. This year also we have applied and we are expecting. And recently I visited Karaikudi Secretary as a summer research fellow in Dr. Pandikumar research laboratory. There I have worked the carbon based nanomaterial for batteries, energy conversion and storage application. These two works are contributed from my research students, Dr. Srinivasan and Dr. Tulasi. And last but not least, I would like to thank my two additional backbones, Dr. A. Kadiravan and my son, Master K. Arun Sashan. Thank you. So if you have any queries, please.
Thank you, madam, for your nice presentation. You have demonstrated how the nanomaterials can be used for biosensor and other applications. Okay, now the floor is open for the discussions. Any queries from the students? From others?
Thank you, sir, for your nice presentation. So I would like to ask in that you have done some microbiological activity for your nanoparticle, right?
Yes.
Have you tested
Micro?
wound healing activity?
Wound healing we have just fabricated.
In which way you have proved?
This one. The Tridax procurements, it's already well known for its wound healing activity. We have just fabricated the bandage, but that is submitted for testing.
Okay. So before going for testing, have you got any ethical approval?
Yeah. We are working with the Crescent Innovation and Incubation Council in Crescent. We have submitted our sample for in vitro studies first. And they have submitted the sample for in vivo.
So in vitro analysis, it has proved?
Yeah, it has proved already.
Okay.
That is with the help of School of Life Science, Dr. Soman Bera.
Okay.
We have the collaboration in our...
Okay. So have you compared with any existing wound healing agent?
In existing wound healing, they are using chemical as a drug as a wound healing activity. But we wanted to replace the chemical drug into the natural one.
Okay.
At the same time, the biomass can be used as a carrier to increase the efficiency of the wounding.
Okay. Thank you.
So we have...
Okay, thank you for a very interesting talk. Just wonder that when you change the source of the biomass to make the carbon dot, will it change the efficiency of the carbon dot, or is it?
Actually, the biomass which contains sugar moieties as well as phenolic alkaloids and flavonoids and all. So the sugar moieties are acting as a carbon core, and the flavonoids and other materials will acting as a reducing agent for the conversion of nucleation into carbon dot structure. That is the proposed mechanism involved.
Thank you.
Thank
you. Any other questions? Okay, ma'am, I have one question. Regarding your first part of your talk, you talked about fluorescence, that thing. So, the fluorescence effect, you done the sensing in aggregated state or in the normal state of your material?
No, not in aggregated state.
Okay.
It's in solution state sensing only. We have done it through the fluorescence quenching studies analysis. Both the steady state as well as the excited state analysis through the lifetime process.
Okay, madam. Okay, fine. So, if there is no more question means, we thank Dr. M. Asha Jhansi for her wonderful presentation. Okay, thank you.
Thank you so much, ma'am and sir. We request Professor Dr. N. Palanisamy sir to felicitate Professor Dr. M. Asha Jhansi ma'am. Thank you. We now request Professor Dr. M. Asha Jhansi ma'am to felicitate Professor Dr. N. Palanisamy sir. Thank you, sir and ma'am. Thank you, sir and ma'am. Thank you. So we will be now having a 15 minutes break. All the refreshments will be served outside. We'll be having a combined session after 15 minutes. Thank you. all the participants to come into the auditorium as the next session will start soon. Request the participants of the oral presentation to submit their presentation in the front desk. I repeat, we request all the participants of the oral presentation to submit their PowerPoint to the front desk. Thank you. Yes. We request all the poster presentation participants to put up your posters near the registration desk, which is outside the auditorium. I repeat, we request all the participants for the poster presentation to put up your poster outside the auditorium near the registration desk now. Thank you. ID இருக்கா யார்?
A kind announcement to all the delegates. I request the following delegates to submit your oral paper presentations in the front desk. The numbers are 16, 52, 53, 59, 60, 63, 70, 71, 72, 75, 78, 82, 83, 84, 138 and 146. If any delegates wish to present and have registered and this information is only for the presenters who is going to present in the Annapurna auditorium alone. Now the technical session will be by Professor Dr. J. Madhavan sir. This lecture will be continued by oral paper presentations. The following delegates will be presenting here, that is in Annapurna auditorium, and other delegates who are about to present will be presenting in the corresponding venues. I repeat the number of participants who will be presenting in Annapurna auditorium, that is 16, 52, 53, 59, 60, 63, 70, 71, 72, 75, 78, 82, 83, 84, 138 and 146. Any new delegates who wish to present and have registered now, please to come to the front desk, and the delegates who have read now, please to submit your PPTs as soon as possible.
A very good afternoon. Now we'll start with the next session. We welcome Professor Dr. J. Madhavan sir, Associate Professor, Department of Chemistry, Thiruvalluvar University, Vellore, on the title Bismuth-based Semiconductor Photocatalyst for Wastewater Remediation. The chairperson for this session would be Professor Dr. M. Sridevi Ma'am, Head Biotechnology, Vinayaka Mission's Kirupananda Variyar, Engineering College, Salem. Over to you, ma'am.
Good afternoon to one and all present here. It's my immense pleasure to welcome Dr. J. Madhavan sir for this INEEBA conference. I'm privileged to introduce him. He is working as an associate professor, Department of Chemistry, Tiruvallur University, Vellore. His research area specialization is nanomaterial for dye-sensitized solar cells, hydrogen evolution reactions and supercapacitors, degradation of aqueous organic pollutants using heterogeneous photocatalyst photophenton reactions and sonophotocalysis for advanced oxidative treatment of organic pollutants. He has received many grants from the funding agencies such as DST-SERP, DAE-BRNS, DBT-MST, Indian government funding agencies for the worth of rupees 1.02 crores. And during NPDF, the project worth is of 19.2 lakhs for the period of 2017 to 2019. He has visited various countries such as Australia, China, South Korea, Malaysia, and Sri Lanka. He has supervised many scholars, and one NPDF scholar has completed his studies, and he has guided for about 7 PhD scholars and 14 MPhil and 30 MSc students. So to add on to his credits, the Google Scholar Citation Indexes is 8,640 and the H index is 51. The I-10 index is 122. The paper publication is, like, he has published about 153 international and 2 national papers in peer-reviewed journals. The cumulative impact factor is 520. The book chapter published is 12, that too mainly in the Wiley, Elsevier and Springer, Taylor and Francis. So he owned 1 patent and he received the certificate of appreciation as one of the top 5% of highly cited authors in Royal Society of Chemistry, UK journals. He is listed in the top 2% scientists announced by the Stanford University, USA, under single year category for the past 3 years. He received the Best Researcher Award from Tiruvallur University for the academic year 21 and 22. He held various positions such as Member Syndicate in Tiruvallur University, Vellore, Academic Council Member, Tiruvallur University, Deputy Director, Center for Accreditation, Tiruvallur University, Coordinator for International Relations Center, Tiruvallur University, member of BOS in Chemistry for Department of Chemistry in Tiruvallur University. Also, he is a member of Rural Society for the Advancement of Chemistry. He is a reviewer in peer-reviewed international journals. Hope, like, we have an eminent person here to deliberate on the title, Photocatalysis. I welcome you, sir.
Hello. Thank you very much, madam, for your nice introduction about me to the audience. Is it ready now? No. Okay. So today I am going to talk about the importance of wastewater treatment, particularly the photocatalytic degradation. So I basically work on the preparation of different nanomaterials for the wastewater treatment applications. Basically, you know very well, titanium dioxide is a very benchmark TiO2 is a benchmark photocatalyst for the wastewater treatment applications. So today I am going to talk about the bismuth-based materials. So first of all, I would like to thank the conference organizers for inviting me here to present my research research topic on research interest on the wastewater treatment. So, and particularly Dr. Anbalagan, who is my friend, invited me to give an invited talk to this prestigious INEEBA conference. So, okay.
So kindly project this PPT.
So I basically from Tiruvallur University, from Vellore. If I say if I am from Vellore, people used to ask, are you from VIT? Vellore Institute of Technology, which is a famous university in Vellore. But our university is a state government university funded by Tamil Nadu government. It is covering the 5 districts around Vellore, Tiruvannamalai, Kallakurichi, Ranikpet and Tirupattur. These 5 districts we cover. We have around 80 affiliated colleges under our control. So Tiruvallur University started under the name of our saint, the poet Tiruvallur. So this is for your information. Okay. Energy.
Sir, could you please elaborate your scholar's work?
Sorry?
Could you please elaborate your scholar's work for some time?
About?
Your PhD scholar's work.
My PhD scholar Tirthagiri is my student here. So, what is that? Dr. Tirthagiri is my first student.
Tirthagiri, sir?
Yeah, Tirthagiri. And Dr. Sendin.
Current research work in Tiruvallur University in your department, sir?
I am now working on the photocatalysis and also the electrocatalytic water splitting reactions to produce hydrogen gas, hydrogen fuel. So we have completed around 7 PhD students. Most of them are abroad. So
all the works are pertaining to this hydrogen gas?
Sorry?
All the works are pertaining to the hydrogen gas, sir?
No. Solar cells, dye-sensitized solar cells. Initially, I got 2 projects on dye-sensitized solar cells. So, Dr. Giri and others, they initially started working on the dye-sensitized solar cells. Later on, photocatalysis. So, I basically from a photocatalysis person for the past 20 years. So, now I have started some energy production, hydrogen fuel generation through water splitting reactions. So basically I work on the cathode materials, so different nanomaterials for cathode electrode replacement applications. Okay, so energy.
Sir, could you please give a gist about the degradation of the aqueous organic pollutants using this photocatalysis process?
That's what I'm going to talk. So if I present...
So then you can give the basic idea about that, because most of them are from students.
Okay. Basically the industries, which textile industries or pharmaceutical industries and other industries which are using the organic compounds, they are the major threat once we release from the industry. So we need to treat them before letting it out into the ecosystem. So for that various processes are available. The conventionally in industries in Tirupur, maybe they are using the biological processes. Biological processes using microorganisms. These are very cheap compared with the conventional processes. So ours is a photocatalysis is a recent technology which can replace when you use some microorganisms, we have a problem of incomplete degradation. So with this photocatalytic technology, we can achieve complete degradation. So, okay. So our equals for the administrative and academic block, and we have 10 departments. It's a young university among the state government universities in Tamil Nadu. Is our under the name of the poet. So these are my this availability of we have 90% water around Earth is salt water. So salt water, Earth is surrounded by the land is surrounded by 97.5% of the salt water. Remaining 2.5% only is fresh water, of which less than 1% is readily available for our use. Remaining 1.5% is not for our reach. So we have only 1% of the water, fresh water, for our purpose. So we need to fresh water. These are the pollution and industrial augmentation, particularly the paper pulp industries, textile and dyeing industries. They use a lot of organic compounds which are very toxic and carcinogenic in nature. So particularly in dyeing industry, you can see during the dyeing process, after the dyeing process, 20% of the dye effluent is released as a effluent. So effluent directly into the ecosystem, that will definitely affect the human being and another animal, micro and also the microorganisms. It will destroy the environment. So we need to treat the water before discharging them into the ecosystem, for which there are many approaches: chemical method, physical method and biological methods. As I said before, biological method, they use microorganisms, which is very cheap. In economic wise, it is very cheap. The physical methods, you have the adsorption method that converts. The problem of adsorption is they simply convert from one phase to the another phase. That is from the liquid phase to the solid phase after the treatment. So after the treatment, we need to treat or do the next processing to completely degrade the dye. So it is a problem. Physical method has some disadvantages. And whereas in the chemical method, we have the oxidation, that is I am going to speak now, that is the advanced oxidation process. Advanced oxidation process is a process, what are all the process that generates the powerful hydroxyl radical. If you generate the hydroxyl radicals, which are non-selective and completely degrades the compound encounters, it will attack the structure of the compound and degrades them to the smaller molecule. So here we have shown a process generate hydroxyl radical. For example, here you have peroxide process and this sonolysis. That means use of ultrasound waves to generate the hydroxyl radicals, and electrolysis. This is a Fenton reagent, Fe2 plus hydrogen peroxide, and photocatalysis. So all these processes generates the powerful hydroxyl radicals. So in today's presentation, I'm going to speak about on the photocatalysis, semiconductor photocatalysis for the as a advanced oxidation for the wastewater treatment. We have several advantages, like as I said before, it's highly reactive, non-selective, and therefore it will react with whatever the organic compound that it encounters into. So, and also it is a powerful oxidizing agent. It's harmless. It's OH dot, harmless. So because of these advantages, it is considered as one of the viable technology or viable method for the treatment of the wastewater. This is the early development of the TiO2 photocatalysis. You can see in 1976, the Gary et al. They used the TiO2 photocatalytic technology for the decontamination of the polychlorinated biphenyls. Later on, Fan et al., they studied the degradation of pollutants like inorganic pollutants, cyanide ion, and also the hydroquinone, the organic pollutants. This is the early development of the photocatalysis process. These are the other applications of TiO2 photocatalysis. For example, we can use this for CO2 reduction reaction and NOx elimination and nitrogen fixation and photocatalytic hydrogen production. So these are all the various other possibilities, various other processes that works under the basic principle of the photocatalytic mechanism. So then we have the homogeneous and heterogeneous two types. So homogeneous is the Fenton Fe2 plus hydrogen peroxide type catalysts are used under the homogeneous photocatalysis, and heterogeneous photocatalysis we have the benchmark photocatalyst, the titanium dioxide. This works on the when the semiconductor is illuminated with a light or particular solar light, it will create electron hole pairs, and the electron is involved in the oxidation process, and hole involves in the electron forms superoxide radical and degrades the organic pollutants, and at the same time hole is involved in the forms hydroxyl radical that will also degrade the organic pollutants. This is the mechanism of the Fenton reagent. You can see here it forms a hydroxyl radical when we combine Fe2 plus hydrogen peroxide. So these are the typical examples of the two processes. Today, in the heterogeneous photocatalysis, we have the following drawbacks. That is, they have a poor absorption in the visible light, and also their electron hole recombination is very fast. The thing is, after the irradiation, if you generate the electron and hole, it should not recombine. We need to make the electron and hole to involve in the oxidation and reactions, then only it is a fruitful reaction. If they recombine, that process is going waste. So to avoid that recombination process, there are various strategies have been applied. For example, metal doping, and also the combination of two different semiconductors, so that the electron and hole they formed, they will interact, they react in the next consecutive reactions and involved in the degradation process. So today we have here the n-type metal. Usually in the semiconductor it is dopant. If you dope the metals, we can, and also non-metals, we can change the energy positions of the donor level and acceptor levels. So, and this is regarding with the metal dopants. Whereas with the semiconductor coupling of the two semiconductors, if they have suitable band gaps, after the illumination, the electrons and holes are efficiently transferred into the next semiconductor level, and they further involved in the reactions. This is one strategy. So today I am going to speak about that semiconductor coupling two different semiconductors for the efficient degradation reactions. Regarding the bismuth, why bismuth? Bismuth exists in a bismuth 3+ states are interested in it, and they have a suitable band gap, that is, they can absorb visible light efficiently than other materials, and they have a layer structure. These advantages makes the bismuth based compounds. These are all the various bismuth based compounds available in the literature. They are a good photocatalyst. So today I am going to speak about on the bismuth vanadium oxide, and nickel ion layered double hydroxide material for the degradation purpose. Bismuth vanadium oxide is a monoclinic primitive, is a tetrahedral structure which I have shown here. The LDH, layered double hydroxide, recently governed a lot of attention among the researchers in this particular field, particularly the photocatalysis hydrogen production. So there are many different applications recently reported on this material, layered double hydroxide structures. In the LDH, we have the two metal ions, 2+ state and 3+ state we have, and also the hydroxide. So anchored on the structure, and anion is kept in between the two. Occupy the interlayer structure. The size of the anion determines the space, the spacing between the two layers. So, and the anion is hydroxide ion is the backbone of the LDH. So the layered structure facilitates the electron hole separation process. As I said before, after irradiation, electron and holes are formed. If they have a layer structure in between, the electrons are efficiently transferred from one layer to the another layer. Therefore, we can prevent the recombination reaction. That is a strategy based on which we have designed this material for the degradation applications. So first we have synthesized the composite material. First we synthesized the nickel ion LDH by using a simple hydrothermal reaction by taking calculated amounts of nickel and iron nitrate and stirred it in hexamethylene tetramine for 30 minutes, and hydrothermal reaction followed by calcination. Then the bismuth vanadium oxide is also prepared and composited with the LDH. At the end, the hydrothermal reaction was carried out to give a layer structure. So, the characterization technique, XRD, shows the formation of the monoclinic phase for bismuth vanadium oxide, which is well matched with JCPD's data, and the nickel ion LDH also shows the cubic phase. When we composite together, we could see the formation of the mixture of two phases, confirming it's the nanocomposite formation. And then we did the morphological characterization, SEM-TEM, and yes, like the bismuth oxide, the layer-like structure for the LDH, and also we can ISR-TEM shows the heterojunction between the two semiconductor materials. They are very close to each other, so its heterojunction formation is formed. And the SAED pattern also shows some the crystallinity of the material prepared. And EDAX confirms that the impurity of the material. No other elements are present after the preparation. That confirms the purity of the synthesized material. And the optical properties are important because we are dealing with light. So the material prepared should absorb the visible light. In order to confirm whether the material can absorb the light, we have taken the UV DRS and the band gap positions are calculated. You can see the 2% LDH loaded bismuth vanadium oxide, that is BVNF2, shows a very low band gap of about 2.44 electron volt among other materials, though it is 1.8 electron volt for the LDH, but the recombination is more if you use. So when we mix that one with bismuth vanadium oxide only, the efficiency of the reaction is enhanced, which the data I will show in the degradation data, I will show in the next slide. And then the photoluminescence studies also confirms the 2% loaded material has a very long lifetime or the very low recombination rate. We can see the intensity of the BVNF2 is very low compared with all other materials. So we can successfully avoid the recombination process when we composite the materials, two materials. And then we carried out the transient photocurrent measurements. We can see the photocurrent generated for the composite is much more than the pure material like bismuth vanadium oxide and nickel ion LDH. That means we can the lifetime of the electron generated is more, so they can involve more in the degradation reaction. Then we calculated the conductivity studies or the Nyquist plot, impedance studies. Nyquist plot shows For the 2% loaded material, the charge transfer resistance is less. That means it has a more conductivity. Therefore, the electron can easily move within the material and involve in the degradation reactions. So that data, if the semicircle is very small, that means it has a very good conductivity and suitable for the degradation application. Then we carried out the photographic degradation data. As I said before, the BVNF2, that is 2% loaded material, has a much more, about 70% degradation within 60 minutes, whereas the pure materials show very less, up to maybe 20% of degradation only. So the reaction follows the first order kinetics. From the plot, we calculated the rate constant. The rate constant for the composite material, particularly 2% material, is much more. In the case of, if we increase the percentage to 2% to 3%, the degradation rate decreased because the added LDH may act as a recombination center again. So the minimum we need to optimize at which percentage of the material is suitable for efficient transfer. That information we can get from these data. And also we carried out the recycling studies for the 3 consecutive cycles. That means once we carried out the photocatalytic degradation reaction, we collect the material again, that is filter the material and dry it, and then how much amount of photocatalyst needs to be added again to maintain the total amount of 1 gram per liter we add, and then we do the reaction. Similarly, for the next 3 cycles, we reused the catalyst, and we could see that not much lowered in degradation was observed. That means the catalyst, the synthesized material is stable. The stability is important when you go for the industrial applications. So our data for the 3 cycles shows the material prepared is stable. Then we carried out the scavenging studies, because in the photocatalysis process it generates a lot of radicals, hydroxide radicals, superoxide radicals, everything is found and holes are found. So which one is responsible actually for the degradation process? That we can identify when you do the scavenging studies. That is, we have taken the radical scavengers like benzoquinone for superoxide and ammonium oxalate for holes, and isopropyl alcohol for hydroxyl ions. So when we take these radical scavengers and perform the degradation experiments, the actual without any scavenger, the degradation is like this. So when we add the benzoquinone and isopropyl alcohol, the degradation is reduced when compared with in the absence of any scavengers. That means when in the presence of isopropyl alcohol and benzoquinone, the degradation is reduced, means these are the radicals responsible for the involved in the actual degradation process, like that is the superoxide and hydroxyl radicals. So based on this information or confirmation, we have proposed the mechanism, like it's the photocatalytic degradation mechanism followed the Z scheme mechanism. That means on irradiation, both the semiconductors forms electron and holes, because they are very close. That is, the valency band of the LDH and the conduction band of the bismuth vanadium oxide are very close. Therefore, they involve in the recombination process, and the conduction band electron and the valence band hole involved in the oxidation and reduction reactions for the pollutants. So like this, the suitable band gap favors the recombination reaction, recombination of electron hole, and another electron hole, remaining electron holes on the involved in the degradation process and successfully degrade the dye. This is the mechanism we proposed based on the radical studies. So coming to the summary of my work, we can see the 2% loaded material, that is nickel ion LDH and bismuth vanadium oxide, showed a very high efficiency, and the photoelectrochemical studies also showed that they be enough to complete as a lower recombination that is responsible for the degradation of the pollute, and also the radical scavenging studies confirm the superoxide and hydroxyl radical play a major role in the degradation of the chosen dye rhodamine by. And finally, the Z scheme mechanism was proposed. So based on these, the stability and the performance and the efficiency of the degradation data, we can use this material for the wastewater treatment application. Is the suggestion I am, is the conclusion I can make from our data. So these are our collaborators. Professor Muthupandi Ashok Kumar, he is my postdoc boss at the University of Melbourne, and Professor Choi is our collaborator involved in the hydrogen production. Recently, electrocatalytic reactions we are performing, and Professor Ara from Malaysia, and Professor Napoleon, who is supporting me. The data presented here today, all from we have taken from SRM University, Kattangaluttur, Chennai. Dr. Napoleon is supporting our research, and these are, I thank my guide, Professor Marudumuthu, who introduced me to in the topic of photocatalysis, and my collaborators and my students. Okay, thank you one and all for the kind attention. Thank you.
Thank you, sir, for your informative session. Hope the audience, they have got good insights about the photocatalysis and the bismuth composites. The floor is open for discussion. Any queries from the audience side?
Maybe all are hungry. All are hungry. It's okay.
It is a nice talk, Dr. Madhavan. Have you done the TOC analysis for the degradation?
Okay. That is the, whenever we do the degradation or wastewater treatment, TOC is the ultimate thing we need to do. That confirms only whether all carbon atoms are converted into CO2 and or mineral acids. That data we need to do further. Actually, our focus is to prepare the new materials. So maybe as in our future work we will do. So for other earlier studies we did, but now we focused on new materials only. So thank you for your suggestion. Thank you.
Any other questions? Sir, like one question from my side. Whether this bismuth composites has been used in dye degradation currently as a commercial products or something like that?
Commercially not yet much studied. So recently they are developed.
It's in research.
Yes.
Thank you so much.
Thank you. Thank you.
I thank the organizing committee of INEEBA conference, especially the Anbalagan sir, for giving me this opportunity. Thank you, sir.
Thank you, sir. I kindly request our chairperson, Professor Dr. M. Sridevi, Head Department of Biotechnology, to honor our speaker for the day, Dr. J. Madhavan, sir. I also request Dr. J. Madhavan, sir, to felicitate our chairperson for the day, Professor Dr. M. Sridevi, ma'am. Thank you, sir. Thank you, ma'am. We'll be starting with the oral paper presentations now. The lunch has been ready. The participants who want to take lunch can please go without making noise and have your lunch. We'll be continuing with the oral paper presentations without a gap. All the delegates, as per the schedule which has been shared to you previously, we request you to go to the halls respectively.